Alright, so today I'm gonna be introducing a benchmark. So the title of this important article is A Comprehensive Graph Pooling Benchmark. Effectiveness, Robustness, and Generalizability. So this paper in 2024. Graph pooling has gained attention for its ability to obtain effective node and graph representations for various downstream tasks. Despite the recent surge in graph pooling approaches, there is a lack of standardized experimental settings and fair benchmarks to evaluate their performance. To address this issue, we have constructed a comprehensive benchmark that includes 17 graph pooling methods and 28 different graph datasets. This benchmark systematically assesses the performance of graph pooling methods in 3 dimensions: effectiveness, robustness, and generalizability. We first evaluate the performance of these graph pooling approaches across different tasks, including graph classification, graph regression, and node classification. Then we investigate their performance under potential noise attacks and out-of-distribution shifts in real-world scenarios. We also investigate detailed efficiency analysis, backbone analysis, parameter analysis, and visualization to provide more evidence. You see an overview of hierarchical backbone for graph classification and regression. So this pool denote a graph pooling function which maps G to a graph, but probably with less vertices in the pooled graph. So the basic updating rule if you use graph convolution is this. So the pooling layer adds to this. So we have graph convolution pooling, and this continues until it reaches the lowest number of nodes, which is suitable for graph classification. For example, these data sets these can be easily available in PyTorch geometric. So we have discussed, for example, mean cut pool, diff cut pool, daemon in the previous videos because they are hierarchical graph pooling. But they also can be used for node classification. For example, for over-smoothing, we usually use dropping method, like message dropping, node dropping. And you see the performance, the mean and variance of average, precision, and accuracy are reported. For example, NCI1 for if you use sag pool, then you have 73% accuracy with this standard deviation. Of course, it is not good that you have a very big standard deviation. It means it's very noisy. Even if you shuffle it, you get something else. So it shouldn't be too much. For example, this is good. The standard deviation is small, and it has a decent number. So these are, you can also use it graph regression and node classification. These are top benchmarks used in 90% of ICML papers, NORIX papers, ICLR papers, AAAI papers, HK papers, ECML papers, ECML PKDD papers. You see these benchmarks. You see it everywhere. Because everyone should compare with the same data set so that we understand which model is performing well. But we don't just look at the numbers, because if you know most of them are overfitted or anything. So the methodology is more important if you want to contribute to ICML conference, for example. So DND another data set, NCI1 another data set. But the micro F1 is better than macro. It's more exact, of course, more difficult. And you can see for example, for Cora dataset, it's available in PyTorch geometric. Then if you use panpool for Cora, then the macro F1 accuracy for panpool is 82%. Then you can also see what happens if you change the convolution methods. For example, going from graph sage to graph attention or graph convolution. So we construct the first graph pooling benchmarks that includes 17 state-of-the-art approaches and 28 different graph datasets across graph classification, graph regression, and node classification. We find that node clustering pooling methods outperform node dropping pooling in terms of robustness and generalizability, but at the cost of higher computational expenses.